Hello, welcome to the lecture series on control systems engineering. In this session, let us discuss about root locus. We'll first explain the importance of root locus plots, then establish the procedure to draw root locus plots. Then we determine gain k for the given transient response specifications. So what is root locus anyway? It's a graph displaying the roots of a polynomial equation when one of the parameters in the equation changes from 0 to infinity. So letting the closed loop characteristic equation be the polynomial equation, one can use the root locus technique to find how a controller design parameter affects the resulting closed loop poles from which one can choose a right value for the controller parameter. What all these mean? Let us understand. See, earlier we have discussed that suppose if I have S-plane, this sigma, this is j omega, and you have a root on the left hand side of S-plane. Then you have seen the response will be exponentially decaying down. And you have called this system a stable system. Suppose if I keep on moving the root towards left, it will decay much faster. Further, if I move, it will decay much faster. So it is something you can say the speed of response changes. And by chance, if you have a root on the imaginary axis, roots on the imaginary axis like this, you have seen the system oscillates continuously with constant amplitude. Suppose if you have a root on the right hand side, the response will be exponentially building up, and you have called it as unstable, right? Because the solution for this will be y is equal to something like e to the power of minus t, and solution for this will be e to the power of plus t. Suppose if you have complex conjugate roots like this, then you have seen it oscillates, amplitude exponentially decays down, and it finally damps down. This is also a stable condition. Suppose if you have roots on the right hand side, then the response will be exponentially building up, and it will be oscillating in the meantime. All these things we have studied. Another very important thing is that if you have S-plane, and this is zeta is equal to 1 line, and this is zeta is equal to 0 line, and these are constant values of zeta like this, correct? Constant values of zeta. And this is zeta omega n, and this is omega d. Correct. We may be looking for something like rise time, peak time, overshoot, and settling time, all this. So the question comes here, where exactly we should locate our roots? Where exactly we should locate our roots in this region, so that the system gives the required rise time, peak time, overshoot, setting time, such time response specifications. Suppose if I have C of S by R of S is equal to, say, K divided by S square, let us say plus 2S plus K. Now this S square plus 2S plus K is equal to 0 is the characteristic equation. Okay, they represent a closed loop. The roots of this equation represent the closed loop poles. If I go on varying the values of K, suppose K equal to 0 in this parameter. So where are the roots located? If K is equal to minus, say, 1, so how the roots move to the next position? So if I go on varying the K value up to infinity, how exactly the roots move, we can find out. Then we can choose the right configuration. So once I know choosing a particular K value, correct? So we can find the position of this closed loop where exactly we can achieve some of these transient response specifications. So that is the idea about this. So if we have a complex system, we can find out the right closed loop configurations, closed loop poles configuration, so that we can meet the transient response specifications. So that is the meaning. Let the closed loop character equation be the polynomial equation. One can use the root locus techniques to find how a controller design parameter K affects the resulting closed loop poles, from which one can choose the right value of the controller parameter. So we can choose the right value of K to achieve the required transient response specification. So that's the idea about the root locus. So is a root locus is the method of graphically displaying the roots of a polynomial equation having the following form on the complex plane when the parameter K varies from 0 to infinity. So 1 plus Kg of S is equal to 0. Then 1 plus K, this is the numerator, this is the denominator of G of S equal to 0. In the numerator, you will have zeros, and in the denominator, you will have poles. Right? So that's the, now we have to find out the roots of polynomials. Right, these are known as open loop, these are known as open loop zeros. These are known as open loop poles. Then when we get the characteristic equation, we get the closed loop poles. Okay, so we'll determine the range of K that have closed loop poles in the performance region. Okay, so this is our transfer function. Let us say G of S is equal to 1 by S into S plus 1, S plus 2. Okay, now the characteristic equation is 1 plus g of s h of s equal to 0. That is 1 plus k divided by s into s plus 2 is equal to 0. Correct? Then if I write this will become s square plus 2s plus k equal to 0. Suppose if I put k equal to 0 in this equation, you will get s equal to 0 and s equal to minus 2. Okay? So, this is sigma. This is imaginary omega, j omega. This is your S plane. Now S equal to 0, S equal to 0 and S equal to minus 2. In this place, the value of K is equal to 0. K equal to 0. Now let me put K is equal to 1 here. Then S square 2S plus 1 equal to 0. If I solve that equation, I'll get S equal to minus 2 minus 0.293. Maybe minus 0.293. Somewhere here you will get, let us say. Minus 1.707. Maybe somewhere here you get. 1 here you get. So this can be K equal to 1. K equal to 1. If I go on varying the values of K, you might get number of poles like this. Next. Like this. As you go on varying the K, go on solving the equation, you are go on getting the roots position. You join all these points like this. Join all these points like this. Okay. Right. This is what you call it as a root locus. Root locus. Okay. So here you have open loop poles. Then as you go on giving the values for K, you get the roots, join them, and you are going to get the poles here, right? What are the closed loop poles? So then plot the locus through all these points, you are going to get the root locus. Okay. The next question comes, what is the guarantee a chosen point is on the root locus? Is on the root locus. Take this point, join this point to the original roots. Okay. Find the magnitude of that. Modulus of G of S, H of S. That should be 1. That should be 1. Also, you measure this angle. Okay, this angle and this angle. That should be 180 degree. Then the point is on the root locus. So once you have this plot, then what is that we can do? You know, Sorry for the disturbance. Now cos theta is equal to zeta. So if zeta is known, we can find theta. So once theta is known, we can measure a value of theta and we can draw zeta line. So once the zeta line is known, what is the value of k we can find out. Okay, from that the corresponding closed loop poles can be obtained. So that's the idea. So this zeta is there, then you know k is there. Once this is there, this is omega d is nothing but omega n under root 1 minus zeta square, and zeta is known. Omega d we can read from here. We can find omega n also. So Tp is nothing but pi by omega d. Okay. So Tp is pi by omega d. Then you know Ts is say 4 by zeta omega n. And Mp, the overshoot, is e to the power of minus zeta pi under root 1 minus zeta square. Yes. So all these things we can easily know, right? So for that, what is the corresponding value of the parameter? Now, once we know that these closed loops are there, then you can bring that back, these closed loop poles, and you can get the characteristic equation. Probably now we can work backwards, right? We know the system parameters. It becomes easy for us to design the system to meet the required specification, right? So that's how we can find, once we have the root locus, then we can find k value, then we can find closed loop pole configuration which meet our transient response specifications. So you see here, as I mentioned here, a point to be a root locus, modulus of g of s h of s must be equal to 1. So very accurately we have to draw this root locus plot, and the angle should be 180 degree. 1 plus g of s h of s is equal to 0, so g of s h of s minus 1. So that's why the angle should be 180 degree. The whole idea is 1 plus g of s h of s is equal to 0 is our characteristic equation, right? So g of s h of s is equal to minus 1 equal to minus 1. So the modulus of this is equal to modulus of this minus 1, that is nothing but 1. So angle of minus 1, so 180 degree. That's why this. So now let us learn properties of root loci useful for construction of root locus plot. How we can construct the root locus plot for a given transfer function. How many root loci should be there? If g of s h of s contain n poles, open loop poles, m open loop zeros, then the number of root loci will be equal to n if n is greater than m. And number of root loci will be equal to m if m is greater than n. Okay. Where exactly root loci start? They all start from poles of g of s h of s. Where do they end? All of them end at respective zeros of g of s, h of s, or at infinity. There are no finite zeros, then the root locus ends at infinity. The root locus plot will be symmetrical about the real axis of the S-plane, right? Portion of root locus on real axis. A given portion of the real axis will be a root locus if the total number of poles and zeros to the right of the section is odd to meet that 180-degree criteria. Then asymptotes of root loci. Number of asymptotes equal to n minus m, difference between number of poles and zeros. The intersection of asymptote is sigma is sum of poles minus sum of zeros divided by n minus 1. The angle of asymptote is given by 2k plus 1 by pi divided by n minus m, assuming k equal to 1, 2, 3, etc. Then breakaway points. If there is root locus between two poles, at one point a break. That is breakaway point. And one root locus will go up, another one will go down like this. Break-in point, root loci from two different poles come and meet at one point. Then one of the root locus will end at this zero, another root locus will be ending at the other zero. If there is a root locus between a pole and a zero, root locus starts from the pole, end at the zero. There is no breakaway in this case. I think angle of asymptotes I have done already. Okay, this is angle of arrival or departure. Okay, whenever there are complex conjugate poles, angle of departure or complex zeros, angle of arrival must be determined. What it means is, suppose you have a complex pole here. So how exactly root locus starts from here? So then we measure the angle of departure. Then we say it has to go along this line. Okay, like this we measure. Then we say it should go along this line. This angle we call it as angle of departure. Same way, if it is a zero, then the root locus will come and meet. So then that is angle of arrival. Okay, this is angle of arrival. This is angle of departure. Right. Intersection of root loci and imaginary axis. So probably you have root locus like this, this is coming this way, this coming this way. The break may a root locus go like this. So it cuts the imaginary axis. So where exactly it cuts? What is the k value at that point? So here the roots will be on the left hand side, then the system will be stable. When the roots come here, it becomes oscillatory. When the roots move to the right hand side, then the system becomes unstable. So this k gives the limiting value. Correct? Beyond this k value, the system becomes unstable. So using these rules, we can draw the root locus plot. Let us draw a root locus plot of a plot for a given open loop transfer function. Okay, the problem here is g of s, h of s is equal to k divided by s into s plus 2, s plus 4. Now, first question is number of root loci. We can very clearly see that there are 3 poles, n equal to 3. There are no zeros, m equal to 0. So number of root loci equal to 3, n equal to 3, because n is greater than m. Where are the starting points of the root loci? One root locus should start at s equal to 0. Another should start at s equal to -2. Another at s equal to -4. So sigma j omega. Then there is one pole at s equal to 0, one at -2, one at -4. So one root locus should start from here, another root locus should start from here, another one from here. Where do these root loci end? There are no zeros. All root loci should end only at infinity. Portion of the root locus on real axis. Now let me show you. This is very important. Now you just keep a plane here. To the right side of this, only one pole is there. One is odd. So there is root locus on this part of the real axis. You go on moving this towards left to the right till it becomes odd only. Suppose if you keep your hand here and to the right, if you see there are two poles, even number of poles, there is no root locus here. Because you have to satisfy that 180-degree criteria. Now after that you come and keep your hand, there are three poles, odd number. Okay, there is root locus here. There is root locus here. So from this pole root locus starts. Indicate this by an arrow. From here also there is a root locus starting and going. What happens next we will see. From here also there is a root locus going like this. Now you see number of root loci is equal to n. Correct? 3 root loci. One starts from here, one from here, one from here. One starts at s equal to 0, one starts at s equal to -2, and other at s is equal to -4. So all should end at infinity because there are no zeros. And how to find portion of root loci I told you. Please don't mistake this line. This line is just assuming that keeping your hand, you are seeing towards right. Okay, so let me erase this out. Okay, right? So that's how we can find the portion of root locus on real axis. Okay. Anyway, okay. I will make this much better. See, this is imaginary axis. This is real axis. Okay. Better take a graph sheet and write j omega s plane. Okay. Next thing is there is a pole here. There is a pole here. There is a pole here. There is a root locus here. There's an arrow this way. This is an arrow this way. There is a root locus here. There is an arrow this way. Fine. Now let us find out number of asymptotes is given by n minus m. Now n is 3 poles, m is 0, so number of asymptotes equal to 3. Intersection of asymptotes sigma a is sum of poles minus sum of zeros divided by n minus m. sigma p minus sigma z divided by n minus m. One is s equal to 0, another one is s equal to minus 2, s equal to minus 4. These are sum of poles. Minus, there are no 0, 0. N is 3, 0. So minus 6 by 3 is minus 2 you get. So minus 2. This is the point where the asymptotes intersect. Okay. Let us now find angle of asymptotes. Is given by theta k, 2k plus 1 by divided by n minus m. If k is equal to 0, pi by 3, it is 60 degree. K equal to 1, 3 pi by 3, that is pi 180 degree. K equal to 2, 5 pi by 3, that is 300 degree. So let us draw one asymptote at 60 degree. Here, draw this asymptote. Okay, right. Next asymptote, you draw at 180 degree. And there is 180 degree. Draw another asymptote at 300 degree. Blue colored one is root locus, green is asymptotes. This red is axis system, that's all that thing, right? Okay, fine. So we have got the asymptotes. Next rule, break waypoints. Now you can clearly see that the root locus is coming from here and coming from here. The root locus is lying between two poles. There should be a breakaway point. Okay? Right. Here, no. There is no breakaway point. Let us find out that breakaway point. For that, take the characteristic equation. 1 plus g of s h of s equal to 0. Then we'll get the characteristic equation. Get k. Differentiate k and equate it to 0. You'll get a quadratic equation. Solve this equation. Then you are going to get 0.85 and 0.315. Go back to the root locus. 0.85 lies between 0 and minus 2 here. Okay, this is a breakaway point. The other one is minus 3.15. There is no root locus there. So you do not have to worry, ignore this. Okay, fine, is the breakaway point. Next thing is, you see here, now I'll draw the root locus. So this root locus is coming from here, this is coming from here, they break. Now these asymptotes help us to go in what direction the root locus should be drawn. So root locus is drawn in such a way, every point should make an angle of 180 degree and the magnitude should be, open loop magnitude should be 1. So one root locus will go like this, another root locus will go like this. And third locus is along this asymptote it will go. Okay, it is assumed that this root locus will meet this asymptote only at infinity. This will meet at infinity. So go on becoming closer to this and draw it out. Okay, let me do that. Okay, now sorry. So it should go asymptotically like this. Okay, now you take here, it is intersecting the imaginary axis at this point. Imaginary axis at this point. Let us find out at what k value it will intersect. For that, get the characteristic equation. Form the root array. As I said, it should be 1 and 8, 6 and k, 48 minus k must be equal to 0, k. So then I have told you earlier, when all the roots on in a particular row are 0, then you will get roots lying on imaginary axis. So 48 minus k by 6 must be equated to 0, so you will get k equal to 48. So that means at that point, this point, k value is 48. K value is 48. So here k value was 0. Here also k value was 0. Correct. Here also k value is 0. Now as I increase the k value, the roots have moved like this. Then one root locus will go like this. And when k is 48 is here. This root locus is here when the k value is 48 here. Here also we can locate somewhere k equal to 48. Correct? Then go on. So k is tending to infinity. K is tending to infinity. K is tending to infinity. Okay. Now I can form the axillary equation now. So what is the axillary equation? 6s square plus k equal to 0. K equal to 48. So s equal to root of minus 8, 2.83. S equal to j omega. Omega is 2.83. At this point, omega is 2.83. Correct? No, omega is 2.83. You can say natural frequency. Correct? Of course, we know the damping in this case is 0. So it should oscillate continuously at that frequency. If I set k equal to 48 in the system, then the system will oscillate, right? With a frequency of 2.83 radians per second. Okay. So for system to be stable, the k value should be less than 48. Frequency of oscillation is 2.83 radians per second. So determine the value of k when the damping ratio of the system is 0.5. Cos theta is equal to zeta, na? Theta is equal to cos inverse zeta. Cos inverse of 0.5, theta is 60 degree. Let us draw 60 degree line. Let us draw 60 degree line. What color to choose? Okay. Measure 60 degree. Now draw a line. Okay, this is zeta is equal to 0.5 line. And this will cut the root locus at this point. What is the k value there? Okay. Product of vectorial distances from all poles and product of vectorial distances from all zeros. Okay. So concerned about the colors. Okay, this color visible, yes. Let us say take this point. From here you draw a line. From here you draw a line. From here you draw a line. That is A. Let us say O. Or you say P, A, B, C. Okay, K should be product of, that is PA, pictorial distances, into PB, into PC. There are no zeros, simply put 1. Measure these values, substitute, you will get K value. Okay, that becomes 8.82. That is the K value. So K is equal to 8.82. Zeta is equal to 0.5. So now you can find what is the closed loop pole. What is the closed loop pole? This is the complex value, imaginary value. This is the real value. So there is one closed loop pole. There is one closed loop pole. Correspondingly, here also we have to find out. Okay. Right, so this is how we can draw the root locus and find the value of K. Now at this K value, for this K value, for this zeta value, what is your peak time? Tp is equal to pi by omega d. So pi by omega d is nothing but omega n under root 1 minus zeta square. You know omega n now. Zeta also you know, you can do it. Otherwise directly you can measure omega d from here. This is omega d. Correct now? You can measure omega d. You can find out peak time. What will be the overshoot of this? E to the power of minus zeta pi under root 1 minus zeta square. Or if overshoot is given, I can find zeta and I can do it reverse way. This is overshoot. What is the time constant? Then 1 by zeta omega n. Then what is the settling time? 4 time constant. So that way I can get the system time response specification. Okay, so that's how we can draw the root locus plot and arrive at the time response specifications. So we will solve some more examples in the next session. Now, thank you.